Welcome back, mathematicians. In this video, we will do more examples where we establish identities. So the first one we are given is sine of angle theta times the expression cotangent of angle theta plus tangent of angle theta, and this is equal to secant of angle theta. Now the left side is more complicated than the right, so we're going to start with that side. We have sine of angle theta times the expression cotangent of angle theta plus tangent of angle theta. What we'll do first is replace cotangent of angle theta and tangent of angle theta using the quotient identity. What this means is I get sine of angle theta times the expression cosine of angle theta over sine of angle theta plus sine of angle theta over cosine of angle theta. Next, we will apply the distributive property. Remember, that's sine of angle theta over 1, so you're going to multiply numerator and denominators together. As a result, what I get is sine of angle theta times cosine of angle theta over sine of angle theta plus sine squared of angle theta over cosine of angle theta. Next, what I'm going to do is reduce by the common factor in the first fraction, which would be sine of angle theta. This now gives us cosine of angle theta plus sine squared theta over cosine of theta. From here, remember, this is cosine of angle theta over 1, so what I'm going to do is multiply that first fraction by a well-chosen 1, and this well-chosen 1 would be cosine of angle theta over cosine of angle theta. This results in cosine squared of theta over cosine of theta plus sine squared of angle theta over cosine of angle theta. We also now have a common denominator, so we can combine this to a single fraction of cosine squared theta plus sine squared theta in the numerator over cosine of theta. We also know that cosine squared theta plus sine squared theta is the Pythagorean identity, which means that it's equal to 1. So I can replace that with 1, and now I still have cosine of theta in my denominator. And then finally, 1 over cosine of theta is a reciprocal identity, and it's equal to secant of angle theta. So I've now officially shown that this left side is equal to the right side. In our second example, we have tangent of angle x plus cotangent of angle x over secant of angle x times cosecant of angle x, and that this is equal to 1. Now we can see that the left side is more complex than the right side, so I'm going to rewrite the left side. That's tangent of angle x plus cotangent of angle x over secant of angle x times cosecant of angle x. My first step is I'm going to replace secant and cosecant with the reciprocal identities, so that would be tangent of angle x plus cotangent of angle x over 1 over cosine of angle x times 1 over sine of angle x. I can now write that as a single fraction in the denominator, so I'll have tangent of angle x plus cotangent of angle x over 1 over cosine of angle x times sine of angle x. Now because I'm dividing by a fraction, I can then change that into multiplying the numerator by the reciprocal of the denominator. This means I have tangent of angle x plus cotangent of angle x, and I need to put that in parentheses, times sine of angle x and cosine of angle x. I'm now going to apply the quotient identities and replace tangent of angle x with sine of angle x over cosine of angle x, and cotangent of angle x I'm going to replace with cosine of angle x over sine of angle x. Still, all of that times sine of angle x times cosine of angle x. Now I'm going to apply the distributive property and multiply this expression to both the terms inside the parentheses. And so what I get is sine squared of x times cosine of x over cosine of x plus cosine squared of x times sine of x over sine of x. I can now reduce by the common factor in each fraction, and for the first fraction the common factor would be cosine of angle x. In the second fraction it would be sine of angle x. This now leaves me with sine squared of x plus cosine squared of x, which is the Pythagorean identity, and it's equal to 1. So I've now shown that the left side is equal to the right side. All right, guys. Good luck!